In the today's lecture, we are going to discuss about the application of J operator method for solving the circuit containing pure inductor. Before going to this, let me tell you something about the basic device, passive electrical device, that is inductor. Let us consider an inductor of inductance L. If I be the current flowing through inductor, and due to the flow of current, suppose phi be the flux linked with the coil of inductor, then we know the flux link with the coil is always directly proportional to the current flowing through coil of inductor, that is phi proportional to I. If we remove the sign of proportionality, put the constant L, so the equation becomes phi equal to L into I, where L is called the coefficient of self-inductance. Now we differentiate the equation number 1 with respect to time. Therefore, after differentiating, the above equation becomes d phi by dt equal to L into di by dt. Let us multiply by negative sign to both the terms. So equation becomes minus of d pi by dt equals to minus L di by dt. Now from the Faraday's law of electromagnetic induction, we can write here the EMF induced in the coil is equals to minus d pi by dt, where the negative sign is given by Lenz's law. According to this, the induced EMF opposes the further change in the flux link with the coil. After putting this minus d pi by dt equals to E, the equation 2 becomes E equals to minus L into di by dt. That is our equation number 3, where L is called the coefficient of self-inductance. And the equation 3 gives the value of EMF induced in the coil or inductor having coefficient of self-inductance as a capital L, and current flowing through the coil is I. Now, whenever the current I is flowing through the coil, the inductor opposes something to the flow of AC through it, and the opposition of non-resistive components like inductors or capacitors for flow of AC is called reactance, and the effective opposition of inductor to the flow of AC is called inductive reactance and is given by XL equals to omega L, or omega is the angular velocity having value twice by F. So inductive reactance is given by twice by FL, where F is the frequency of AC signal applied to the inductor, and this reactance is analogous to resistance. Only difference is that here the opposition of resistance is frequency independent, while the opposition of non-resistive components like inductors or capacitor are frequency dependent, but having the same unit as a ohm. Okay, now let us apply the J operator method for a circuit containing pure inductor. Let an alternating EMF capital E equals to E0 sine omega t be applied to pure inductor having inductance L. We know E equals to E0 sine omega t be an imaginary part in the expansion of complex EMF E equals to E0 small e to the power j omega t. Hence, the complex EMF applied to the circuit containing pure inductor is E equals to E0 small e to the power j omega t. So, with the application of this complex EMF E to the circuit, the current I is developed or flows in the circuit. Okay, current I is flows in the circuit across the coil of inductor, and we know whenever current I is flowing through the circuit, the flux is linked with the coil, and the flux linked with the coil is directly proportional to amount of current. Therefore, the EMF is induced in that coil, which is calculated in the previous article. So, the EMF due to the flow of current I in the circuit containing inductor only, the EMF induced across L, that is coil of the inductor, is small e equals to minus L into d phi by dt. That is our equation number 2. Okay, but this induced EMF further opposes the applied AC voltage. So the sign of applied voltage and induced EMF are opposite to each other. Hence, we can write capital E equals to minus small e. Now put the value of this small e from equation number 2. Okay, therefore the value of applied voltage obtained as E equals to minus of minus LDI by dt, where negative got cancelled, so E equals to capital L di by dt. Now put the value of this applied EMF from equation number 1, which is E0 small e to the power j omega t equals to L di by dt. Now interchange the LHS and RHS of this equation. Just put the L di by dt on LHS and E0 e to the power j omega t on RHS. Send this L on denominator of the left hand side. So the equation becomes di by dt equals to E0 upon L small e to the power j omega t. Now separate the variables, that is equation becomes di equals to E0 upon L into e to the power j omega t into dt. Okay, our principal aim in solving that equation or in solving the circuit is to calculate the instantaneous current flows in the circuit. Okay, so for that, let us integrate this equation. So after integration, the equation becomes in integral sign di equal to E0 upon L out of the integral in integral sign e to the power j omega t dt. Here the integration of di is E0 upon L as it is. Integration of e to the power j omega t will be e to the power j omega t upon j omega, that is derivative of j omega t, that is j omega. Okay, so the equation becomes I equals to e0 e to the power j omega t divided by j omega l, that is our equation number 3. Okay, now we can here write j as j equals to 0 plus 1. Okay, or 0 plus j. Okay, so in place of the 0, now we put cos pi by 2, because cos pi by 2 equals to 0 plus j as it is and j into 1. So the value of equation remains same, and in place of 1, let me put here sin pi by 2. Okay, because sin pi by 2 equals to 1 and cos pi by 2 equals to 0. So the j can be written as cos pi by 2 plus j sin pi by 2. Okay, now use the De Morse theorem, which is cos theta plus j sin theta equals to e to the power j theta. Okay, here j is analogous to the imaginary number I used in the complex algebra and having value of under root of minus 1. Okay, so the this equation simplifies to the form j equals to e to the power j pi by 2. Okay, now put the value of this j in the equation 3. So the resultant equation becomes I equal to E0 e to the power j omega t upon omega L as it is into, in place of j we have substituted e to the power j pi by 2. Okay, now send this e to the power j pi by 2 in the numerator side. The equation simplifies to the form I equal to E0 upon omega L into e to the power j omega t into e to the power minus j pi by 2, because we have taken this j pi by 2 from denominator to the numerator. So here negative sign arised. Now basis of these two terms are same. So the equation can be simplified as E equals to capital E0, I equals to capital E0 upon omega L E, and take the j from both the terms common, j in bracket omega t minus pi by 2. Okay, but in this equation the term E0 upon omega L, here E0 as we know is the peak value or amplitude of AC voltage applied to the circuit. Okay, so it is similar to the voltage, and omega L is the inductive reactance, that is opposition of inductor to the flow of AC, and as we have discussed that it is analogous to resistance. So ratio of amplitude of voltage or the peak value of voltage to the quantity analogous to resistance, so it is a, the resultant quantity can be written as current I0. So E0 upon omega L equals to I0, called peak value of current or amplitude of the current. Let's put this quantity in the above equation. So the resultant equation becomes I equals to I0 small e to the power j in bracket omega t minus pi by 2. That is our equation number 4. Okay, here finally we have obtained the instantaneous value of current by solving the circuit containing inductor. Okay, initially we have applied the AC voltage having EMF equals to E0 e to the power j omega t, and the instantaneous value obtained in the circuit is I equal to I0 e to the power j omega t minus pi by 2. Whenever we compare the equations 1 and 4, so the quantity E is analogous to I, E0 analogous to I0. Obviously, I0 is having a less value as compared to E0, because I0 equal to E0 upon omega L. Okay, so the amplitude of instantaneous current decreases. Now let us discuss about the phase. Here the phase of applied AC voltage is omega t, and the phase of instantaneous current will be omega t minus pi by 2. Okay, so we can see here that the phase of instantaneous current decreases by amount pi by 2. So from equations 1 and 4, it is clear that the current in pure inductive circuit lags behind the applied EMF by a phase of pi by 2. Okay, that means the phase of current is less as compared to phase of the applied voltage by the value of pi by 2. Okay, so whatever may be the initial value of phase of the applied AC voltage, the phase of induced current or the instantaneous current in the circuit decreases by pi by 2. Okay, so it is about the today's article. Thank you very much.